Anything that's not clear in the homogeneous catalysis, the steps, the role of coordination complexes, the insertion, the nucleophilic attack, the ligand association, the ligand dissociation. And we also talked about oxidation or reduction. We talked about oxidative addition and reductive eliminations. And we gave you lots of catalytic cycles and showed you how these various steps play in the conversion of the reactants to the products that is facilitated by the presence of a coordination complex. Anything that's not clear, anything that requires a revision. Of course, once you see the sample exam, you'll get some kind of an idea, like what you're missing. But for now, really conceptually, if there is anything that you find it not convincing enough, I'll be more than happy to go over that again. If not, we'll continue with the next topic. There are two topics that we need to cover today. One is the polymerization catalysis. As you know, polymers are extremely important commodity in the materials market. Uh, Clearly, polymers has dominated the societies across the world, and tons of polymers are being produced. And you may not, or may not realize the importance of inorganic chemistry, because most of the polymers or the polymerization catalysts happen to be inorganic catalysts. So let me give you one example of that, which is a Nobel Prize winning Ziegler-Natta catalysis. Okay. So how the polymerization works here. So let me go to the board if I can see it. Um, so this is the Ziegler-Natta catalysis. What I read in the literature is this is an accidental discovery. It was not intended for this, but somehow they just stumbled upon it by accident. So the catalyst here is if you have ethylene, and if you pass ethylene onto titanium chloride, TiCl4, which is the titanium 4 chloride, in the presence of tetraalkyl aluminum, when you pass ethylene, you get polyethylene. This is such a very important transformation, the polymerization initiated by the presence of titanium and aluminum here. And if you change the titanium to tin or the aluminum to silicon, the reaction won't work. This is a very specific combination, and this has a lot of commercial importance because polyethylene is used in a variety of applications in society. And, and this gives you a very stereo-specific polymerization. Not only ethylene, you can also put dichloroethylene, or you can put chlorobromoethylenes. So you can modify the reactant molecule in different ways. And most of the times you end up having a very stereo-specific polymer. And this is of extreme industrial importance, right? So this is something that you should be aware of. And Ziegler-Natta got Nobel Prize for the discovery of this very important material. The next thing that we want to talk about is what we call the heterogeneous catalysis. So that's what we're going to talk about. So let me find my eraser here. Should be someplace. Heterogeneous catalysis. In the previous lectures, we talked about homogeneous catalysis, where the reactants and the catalyst are in the same phase. And we looked at a lot of industrial examples. And equally important in industry is what we call heterogeneous catalysis, where the catalyst and the reactant happen to be in two different phases. In most cases, what happens is you have a solid catalyst, and what you do is you have a reactor in which you load the solid catalyst and you heat the solid at some temperature. 400, 300, 200, whatever temperature is. Compared to homogeneous catalysis, heterogeneous catalysis can be carried out even up to 600 degrees Celsius. We'll give you some examples of heterogeneous catalysis because industry loves it. So the way it happens is you pass the reactants over the surface of a catalyst and out comes the product. So convenient. Industry loves it because you don't need to separate the catalyst from the product or the reactants. And the only job you need to do is you need to find a good catalyst, which is specific and operates at a lower temperature, lower pressures, and something that you can keep on using for longer periods of time. So there are a great number of examples in industrial catalysis where the catalyst happens to be a solid. So we're going to look into the processes, variety of industrial processes, and give you some idea about how this happens. All right. So that is the beauty of heterogeneous catalysis. Now, the most important thing of heterogeneous catalysis is a solid. That happens to be invariable and inorganic material. Right. So that's what we're going to focus our attention today. So let me give you some ideas about how many different types of heterogeneous catalysts are there to begin our lecture. So heterogeneous catalysis can be classified into three different types. One is what we call bulk catalysis, or sometimes they're also called uniform catalysis. An example of this is zeolites. Although majority of the heterogeneous catalysts are surface driven, you still have catalysis by zeolites. Zeolites are nothing but silico aluminates. So if I have SiO2, Al2O3 composite materials in different ratios and different crystal structures, these are bulk catalysts. In other words, the entire material, not just the surface, but the interior of the solid also serves as a catalyst. So these are called bulk catalysts. And there are others called surface catalysts. In this example, the catalyst, although it's a single phase catalyst, only the surface of the catalyst serves as the primary source, but the bulk does not have any effect. So an example of this is going to be gamma aluminum oxide. Okay, so if you take any acid catalysis, gamma aluminum oxide is used extensively in industry. This is a defect spinel type compound. It's a very different form. Aluminum oxide has a lot of polymorphs. This is one of the polymorphs. The other one is corundum, which is an extremely low surface area material that is not used in catalysis because for all heterogeneous catalysis, you need to have a very large surface area. The higher the surface area, the more efficient the catalyst is. And finally, we have a mixed phase catalysis. In a mixed phase catalysis, typically you have, let's say, iron on aluminum oxide, Al2O3. Or you may have a catalyst called cobalt on TiO2, titanium dioxide. So these are all multi-phase catalysts, which implies that you have a metal that is impregnated into a matrix. The matrix is inert, but still the choice of the matrix is very important for the catalysis. In other words, the support, which is like TiO2 or Al2O3 here, are very important to enhance the catalytic activity of the metal that you do. So there are a variety of metals, transition metals that they use. You can use iron, you can use cobalt, you can use nickel, you can use copper. You have also catalysts in which zinc is also dispersed into the supports to enhance the catalytic activity of the materials. So we're going to give you an idea about different industrial processes. But before that, we'll also talk a little bit about the source of catalytic activity and all that stuff. All right. So in the case of zeolites, what we have here are three-dimensional network solids. That's what the zeolites are known for. So when we say 3D network solids, so in other words, these are crystal structures with a lot of open pores. So these are the channels that you have in the catalyst, and you also have cross-section of the channels like this. So this is a three-dimensional network of silicon oxide and aluminum oxide. So how do these catalysts perform? Number one, you can vary the size of the pores here anywhere between 7 angstroms to almost up to 120 angstroms. By changing the templates and by changing the synthetic conditions, you can make several silico-aluminates with varying sizes of the pores. So you can design the catalyst in a way that only the molecules that fit the pore size will go, others will be discarded. So in other words, these can serve like what we call sieves. So these are molecular sieves. They can filter different sizes. So it's a very important area of catalysis. Now, if you look at the chemical idea here, here is how the catalysts work. So if I have silica network, so this is the three-dimensional network that I'm writing. You all know silica is in 4+ oxidation state in SiO2. But then when you replace one of the silicon with aluminum, aluminum is only 3+, right? So what's happening now? We have a imbalance of charges. I have silicon in 4+ and an aluminum in 3+. For charge compensation, what these materials do is they borrow a proton. Protons have +1 charge. So when you combine the aluminum 3+ with the proton positive charge, the total is 4+, which is exactly what you have in the silica. So in almost all silico-aluminates, you have a free proton. A free proton is equivalent to having an acid. So these are what we call solid acids. Most of the time you're familiar with nitric acid, sulfuric acid, perchloric acid. These are all liquids. But then if you want to have an acid in a solid, zeolites are the excellent examples. Believe it or not, the acidity of some of the zeolites is as strong as, or even more stronger than sulfuric acid. So for all your organic transformations, wherever you're adding liquid acids, you can use these zeolites to do the same thing without using sulfuric acid. Sulfuric acid, as you all know, is very corrosive, right? So in industry, you don't want to use lots of nitric and sulfuric or perchloric acids or hydrochloric acids. So you can have the same type of acidity, sometimes even stronger, just by having a variety of zeolites, which are silico-aluminates. And then on top of it, when you structure or engineer or do the architecture of the materials with selected pore sizes, you now have a great variety of catalysts with different acidities and different pore sizes. So for that reason, in petroleum industry, silico-aluminates are one of the very important class of catalysts. And there are companies in California that specialize in manufacturing zeolites for the petroleum industry. A lot of organic transformations that happen in the fine chemical production in the petroleum industry require zeolites, and there are companies called Catalytica corporation. There are, of course, small companies too. They specialize in supplying the zeolites for the petrochemical industry. This is a huge business. It's a multi-billion-dollar business. And the point that I'm trying to make here is this is the course in advanced in organic chemistry, and you see the importance of these elements in the formulation of this multi-billion-dollar catalytic industry. All right. The next thing that I would like to do is give you an idea about what happens in the acid catalyst. So, suppose if you take aluminum oxide, remember the gamma form of aluminum oxide, which is what I call a defect spinel. Remember, we talked about the structures of spinels in solid state chemistry, where we said the spinels are Ab2O4. If you remove AO from this spinel's formula, you end up having B2O3. That B2O3 is similar to the Al2O3. Here, A and B are arbitrary metals, not boron. B stands to a different transition metal. A could be alkaline or alkaline earth metals. Okay? So you can make gamma aluminum oxide, which is a good catalyst. On the other hand, if you take alpha aluminum oxide, which is called corundum, that's not a good catalyst. It's not a catalyst at all because it has an entirely different crystal structure, which is a rare earth type of C-type rare earth structure. We're not going to get into those things, but structurally it's very different. Catalytically, it is inefficient. So nobody uses alpha aluminum oxide, but it's a gamma aluminum oxide that is extensively used in industry. So here again, I want you to emphasize, it's just not the chemical. It is the crystallographic phase of that chemical that is extremely critical for the catalytic efficiency. So the way we make the gamma aluminum oxide is to take aluminum oxyhydroxide. Aluminum oxyhydroxide has a formula like this. So you can prepare this by taking alkoxides of aluminum and hydrolyze them in a controlled way. This is how you make them. As you can see, aluminum is 3 plus, oxygen is 2 minus, hydroxide is 1 minus, so this is charge balanced. When you thermalize or heat this compound at very low temperatures, about 100 to 150 degrees Celsius, you make the gamma aluminum oxide. This has extremely high surface area. Surface areas are measured in the unit meter squared per gram. How many square meters of area that is available per every gram of catalyst. And these gamma aluminums have about 900 to 1,000 square meters per gram. I want you to physically imagine the space of 900 square meters, and the amount is 1 gram. So 900 square meters, it's almost like 1 gram of material having a floor space of a huge building. That's how you can imagine. So these are all great catalysts. And the value here, 900 or 150, generally determines the overall catalytic efficiency. For most industrial processes, people would like to use the surface area that is very high, right? And you have to make sure that it maintains structural rigidity so that this value does not change when you carry out the reactions. So what happens here in this material is, if you have aluminum contacts, these are the aluminum oxides, on the surface, aluminum attached to hydroxide, and this is another hydroxide on the surface, hydroxides, and this is of course a three-dimensional network. So when you heat them at 100 to 150 degrees, what happens is some of these hydroxyls undergo condensation reaction and give you a surface that is something like a bridging oxygen there. That bridging oxygen there will have 2 electrons So it can serve as a great Lewis base. On the other hand, you can also have some of the hydroxides, and this proton of the hydroxide can give you acidity. So by controlling the temperature, you will be able to have both acids as well as the base sides. So acid comes from the hydroxide decomposition or dissociation, and the oxygen here comes because of the condensation of the two hydroxyls going away, leaving the water, and give you a surface oxygen, which is basic. So you see how beautifully people design the same material with different acid-base properties. You can't use the pH measurements on these solids because they are not liquids. But however, they have strong protons on the surface, which is very important for a lot of catalytic transformations. All right. So how do heterogeneous catalytic reactions happen? Remember the homogeneous catalysis, we had 5 different ways a catalyst can work. For example, we talked about oxidative addition, reductive elimination, oxidation reduction, ligand association, ligand insertion, so on and so forth. Similarly, in heterogeneous catalysis, we have 5 different types of steps. The first step in heterogeneous catalysis process is the diffusion of reactants onto the surface. So for most part, heterogeneous catalysis is a surface-driven process. Okay? So what happens is when you have the solid here, this is the catalyst, and you have gas molecules all around it. What you want is you want the gas molecules to diffuse towards the catalyst. So that first step is the diffusion of the reactant onto the surface of a catalyst. The second step is what we call adsorption. Not absorption, but adsorption. Adsorption is a physical process, could be physical or it could be chemical, wherein the reactant molecules get attached to the surface of the catalyst. If the attachment is strong, we call that chemisorption. If the attachment is weak, like van der Waals forces, we call that physisorption. So physisorption is a weak adsorption, chemisorption is a strong adsorption. So in both cases, you have catalysis happening. So adsorption of reactants on the surface. So the third step here is the diffusion, surface diffusion. And reaction. So for example, if you want to have production of ammonia from nitrogen and oxygen, nitrogen and hydrogen, you will have a catalyst. That catalyst should have the ability to bring the nitrogen and hydrogen closer to the surface. Not only do they bring these gases close to the surface, they also break this. In other words, you will have the nitrogen plus hydrogen. When they come onto the surface, they break the nitrogen-nitrogen bond and make what we call nitrides. And similarly, we also break the hydrogen into hydrides. So what happens now is the nitrogens and the hydrogens migrate on the surface of the catalyst, making ammonia, NH3. Okay, that's a very important step. So there are 2 things that are happening. Those of you who are watching this very closely. The first thing is dissociation of the gases on the surface. And then there is a migration of the species on the surface. And finally, this migration leads to the formation of the product. So this is a very important step in all heterogeneously catalyzed processes. The fourth step is desorption of products. This is also a very important step. Once you make the product, if the product hangs on to the catalyst surface strongly, that's not a good catalyst because it's blocking the next set of nitrogen and hydrogen to come and react and make ammonia. So you want a catalyst, as soon as you make the product, that product must diffuse from the, or dissolve from the surface. And finally, once the product dissolves is the opposite of absorbs, it should be able to diffuse away from the catalyst surface. So diffusion of the products away from the surface. See how beautiful this process is. Majority of the heterogeneously catalyzed processes have these 5 steps. So diffusion of the reactants under the surface, adsorption of the reactants. Adsorption can be physisorption or chemisorption, depending on the strength of attachment. And then once that happens, the surface diffusion and reaction is a very important step, where the species that are absorbed by the surface of the catalyst migrate very freely on the surface. In the process, they make the product. And once the product is made, the 4th step is desorption of the products from the surface, and then diffusion of the products away from the surface. So these are totally different type of steps compared to homogeneous catalysis. If you compare these two processes, you know that the mechanism of the catalytic action is very different on heterogeneous catalyst relative to a homogeneous catalyst. And very important thing is, of course, the surface diffusion, I said, and the reaction. This is a very critical step. And the efficiency of the catalyst, again, is measured by you need to have a lower temperature, lower pressures, and higher turnout and high specificity. So these are all the requirements. And more importantly, we also need to have a catalyst that's robust. It should not be contaminated by impurities of the reactants. So any catalyst that's very robust can handle this. A typical example of a heterogeneously catalyzed reaction that's familiar to all of you is your catalytic converter in your automobiles, where you have after the fire the engine, you get all the unburned hydrocarbons, unburned carbon monoxide, oxides of nitrogen, oxides of the sulfur. And if you don't have a catalytic converter, all of these things will escape into the atmosphere, causing severe pollution. So we have a catalytic converter in your automobiles where you take all these gases from the engine onto the catalyst converter, which oxidizes all these gases into innocuous oxides. For example, if you send carbon monoxide, what you get out is carbon dioxide. If you take any of those unburned hydrocarbons, CXHY, in the presence of oxygen, you get CO2 and H2O. Similarly, if you have any nitrogen oxides, which are again pollutants of the atmosphere, a catalyst converter will convert that into nitrogen and oxygen. So most of your catalysts in your automobile engine are oxidation catalysts. And they operate at very high temperature, which is provided by your engine exhaust gas, right? When you fire the automobile, you have very high temperature in the engine. So that temperature is enough for the catalyst to perform. And in the thing, you get innocuous gases like carbon dioxide, water vapor, nitrogen, and oxygen. So if your catalyst converter is not good, some of the carbon monoxide will still be present. And that's what the motor vehicle inspection station detects and gives you a fail, because you failed the exhaust gases. So this is a typical example of a heterogeneous catalysis process. So in here, we have mostly platinum or rhodium or iridium. These are all expensive metals. Of course, luckily, we don't need to use tons of it. We use extremely small amounts of it, but still they're very efficient on aluminum oxide. So you make a monolith of aluminum oxide, deposit extremely small amounts of platinum or rhodium or iridium. Once you do this, build the catalytic converter, you get all these things. Now there is a huge demand for taking those old automobiles, take the catalytic converters, and recover all this noble metals such as platinum, rhodium, and iridium, which are very expensive. So there are a lot of companies now specializing in recovering the precious metals from spent catalyst converters. And in some countries, I hear that they are even stealing the automobile exhaust converters because there are so many precious metals, they can make cheap money there. Okay. So that's again the importance of the catalytic converters. So there is a lot of demand now to see if you can somehow get rid of these expensive metals like platinum, rhodium, and iridium. Not only they are expensive, they're also not abundant in the planet. We don't have enough platinum. All the platinum that we use in the catalytic converters comes from South Africa, right? So we don't have too many reserves in the US of the platinum stuff. So we just need to import. But if you can find a catalyst that is superior than what the platinum is doing, then you are in multi-billion dollar business. So there's a lot of search going on for the last 20 years to remove and replace the most expensive metals with cheap materials like, like, can I use iron oxide? Can I use iron, cobalt, nickel? Unfortunately, they don't work as efficiently as the platinum does. But still, there is a lot of opportunity for those of you young minds to work in this area. Of course, like companies like Johnson and Johnson, Johnson and Matthey, they are constantly looking out for replacements for these metals. So again, that knowledge comes from inorganic chemistry. All right, so the next thing that we need to touch base upon in the thing is what makes catalyst a good catalyst? A good one. Let me illustrate that by giving you an example of the decomposition of formic acid to carbon monoxide and water. This is the uncatalyzed reaction, and this is very slow. If you want to speed up the decomposition of formic acid to carbon monoxide and water, you need to use a metal catalyst. Okay. People have used several metals. And what they have done is they looked at the heat of formation of the metal formate and the temperature of the decomposition and plotted a graph. Temperature of decomposition and delta H 0 of the metal formate complex. What they found was when you do different metals, you have a volcano-shaped graph here. On your left-hand side, you have gold, you have silver, you have palladium, you have rhodium, and you have platinum on the top, and you have ruthenium, copper, nickel, iron, and tungsten. What is happening here is metals that have very low heats of formation, that means the affinity between the metal and the formic acid is very small, those are not good catalysts. On the right-hand side of your volcano, you have transition metals that have very large heats of formation. They are not good catalysts either. So what you want to have is one that is moderate, neither too small nor too high. So in the decomposition of formic acid, people find platinum is a superior catalyst because platinum has the right heat of formation, neither strong nor weak relative to other elements. So whenever you do catalysis, if you're doing research in catalysis, this is something that you want to focus on. What is the affinity of my catalyst towards the reactant? Is it forming a strong, is it affinity is too strong or too weak? In either case, that's not a good catalyst. You want something that is moderate, that is in between the strong and the weak. So, as you can see, this is very frustrating. And another frustrating aspect of heterogeneous catalysis is the lack of our ability to examine exactly what happens on the surface of a catalyst while the reaction is going on. The reason for this is most of the heterogeneously catalyzed reactions are carried out at very high temperatures, and we don't have any surface analytical tools that can examine the surface of the solid at such high pressures and temperatures. We just don't have it. Most of the surface analytical tools that can look at the surface carefully require extremely high vacuum and low temperatures. So majority of the processes, the heterogeneous catalyst processes, I would say is a speculation. Although we don't know exactly how the reaction happens, we don't have any proof, but we only can give an educated guess. Maybe this is what is happening on the surface that leads to the formation. Sometimes people also look at the activation energies for the reaction versus bulk properties such as electronic conductivities, magnetic transitions, a variety of indirect ways. So this is the disadvantage of heterogeneous catalysis. On the other hand, in the homogeneous catalysis, as you know, we can isolate various intermediates in the cycle and characterize them and propose a mechanism based on that. So that's a big difference between homogeneous and heterogeneous catalysis. Regardless, there are a lot of industry people, they say, we don't care how it works. We just want to know if it works. So they don't really need the mechanism. They want to know a catalyst that will do its job, right? So this is one of the frustrating things about heterogeneous catalysis. But having said that, let me now get into a variety of industrial processes that are given here. One of the important things is hydrogenation processes. Hydrogenation of unsaturated hydrocarbons. Okay, so there is a Sabatier, Paul Sabatier discovered this process accidentally. Most of the heterogeneously catalyzed processes, the discoveries are purely accidental. All right, so I just want you to keep that in mind. There is no, in fact, what Paul Sabatier was trying to do was he was trying to make nickel and ethylene complexes. All right, when he was trying to make nickel ethylene complexes, what he found was he was able to saturate that double bond in the C2H4 ethylene to make ethane. That was unbelievable. If you change this nickel to cobalt or iron or copper or tungsten, this reaction won't work. So the nickel here is a magic catalyst, and it's even used today in industrials. It's called Sabatier process, where you take the finely divided nickel, extremely dispersed. This is called Rani nickel. So very small, tiny, what they call nano-sized particles of nickel. What the nickel does basically is one nickel binds to the ethylene molecule. Now, if you really look at this part alone, this nickel to ethylene bond reminds you of a homogeneous catalyst, right? There is a complex formation using this metal nickel and ethylene. Similarly, the next nickel will have the hydrogen, so it will break the hydrogen into hydride anions or hydride ligands. So you have now three nickel complexes with different ligands. One is ethylene, one is hydrides. So these hydrates then migrate onto the ethylene to make C2H6. Again, students, please understand this is just a proposed mechanism. Do I have any evidence for this? No. Does anybody have any evidence for this? No. So I want you to keep that in mind when you're looking at these processes. Next, and the most important heterogeneously catalyzed process is what we call the Haber process. You must have heard about this reaction here. N2 plus 3H2 giving 2NH3. All right. So if you look at the various thermodynamic parameters for this, the free energy change is about negative 16.5 kilojoules per mole. It's exoergic process. And the delta H for this process is about negative 46.1 kilojoules per mole. So if we now look at these processes, clearly the reaction is spontaneous because delta G is negative, right? And now if you look at the delta H, it is exothermic. So what happens if you carry out the reaction at extremely high temperatures? Which way would the reaction shift? Because this is an equilibrium process. When you carry out the reaction at very high temperature, would the reaction go to the right or the left?
It's going to go to the left.
Go to the left. You're absolutely correct, sir. Is that what we want? Now, so you want to have a catalyst that will work at lower temperatures, as low as possible. But here is the catch. If you look at the nitrogen, this is a triple bond nitrogen, and the bond strength here is about 900 kilojoules. So at very low temperatures, it is nearly impossible to break the nitrogen-nitrogen bond. And to make ammonia, you need to split the nitrogen into nitrogen atoms before you can combine them with the hydrogen-hydrogen. The hydrogen-hydrogen single bond is not as strong as an NN triple bond. This is only 200 to 300 kilojoules, while this is about 900 kilojoules. So this is one consideration. So you can't use extremely high temperature. You can't use extremely low temperature either. So what people use here is a catalyst that is iron on aluminum oxide. So this is a multi-phase catalyst. So when you use iron on aluminum oxide, what people found was you can get a very decent conversion at temperatures of 400 degrees Celsius. 400 is still high. 400 is high, but that's about the optimum. If you go any lower, you will not be able to break that N bond. And if you go any higher, then you're going to split the ammonia back into N2 and hydrogen. That's the optimum. And the pressure here is about, I'm just giving you approximate values, about 100 atmospheres. This is again a Nobel Prize winning discovery where Haber was accidentally stumbled upon this sand here that had some iron. When he tried to dry this sand with hydrogen and nitrogen, he smelled ammonia, as the legend goes, and that's how the catalyst was discovered. So this is the best catalyst. Now, people have been working on this catalyst for almost, I would say, 70, 80 years. They were not able to replace any of the iron. Although recent studies at the MIT found that you should be able to make uh, dinitrogen complexes of molybdenum at negative 10 degrees Celsius, which is really magic. If you were to believe that, that's going to be a game changer. But there are a lot of obstacles in terms of commercialization and all that. But for now, even today in industry, they use iron and aluminum oxide. So since you can't tweak the iron, so people started tweaking aluminum oxide. The aluminum oxide here is a support. What this basically does is it does not allow the iron to congregate and make bulk iron. It kind of keeps the iron separated. That's the job of an anchor. However, when you put small amounts of potassium into aluminum oxide, it tremendously improves the catalytic efficiency of the iron. So these are all secondary interactions. So in this case, the potassium is called a promoter. It's not a catalyst, but it enhances the efficiency of a catalyst indirectly. So potassium, sometimes they use sodium. I mean, if you really look at the composition of the industrial catalyst, most of them are patented. They have cocktails of different transition metals here. So they keep playing with different compositions to see which one gives you the better. Unfortunately, there are no models or theory that helps us to design the catalyst. It's mostly about trial and error. So you try this, okay, if it works, good. Change the other thing if it doesn't work, good. So this is the game. If you are in the business of heterogeneous catalysis, be prepared for lots of frustrations, because whatever changes you try to make, they kind of bring down the catalytic efficiency. So they keep trying different materials because there's no theory that will guide you. Okay, this is what we should be doing here. It's mostly trial and error, and most of the catalysts that we're talking about here are discovered by accident, not by design, not by deep scientific thinking or theory. No, these are all purely accidental. So, to a part, a lot of people believe catalysis is more of an art than science. You need to have a green thumb, and some people are very good at the design, and they can't explain to you why this works because there are no tools. So I can't repeat that enough. So the way we do this is, once the ammonia is formed, what we do is we liquefy the ammonia to ammonia liquid. When that happens, what happens is the equilibrium now keeps shifting to the right because you are condensing the gas to the liquid. This is how you improve the performance. So this is a teamwork of a chemist and a chemical engineer. That is generally the tendency with all catalytic processes. You have teams of chemical engineers and teams of chemists working together side by side in the design and the testing and the evaluation of a variety of catalysts that are used in industry. The next thing is one of the important reactions. As you know, ammonia is one of the um, chemicals that are produced in largest quantities, right? Remember when we looked at the top 10 chemicals produced in the world, ammonia is number 1 or 2. The next one is sulfuric acid. Even the production of sulfuric acid requires a catalyst. Without a catalyst, you can't do that. So let's now look at the oxidation of sulfur dioxide. So the process we're talking about is sulfur dioxide plus oxygen giving sulfur trioxide. One of the biggest problems is this reaction is extremely lousy. Without a catalyst, the efficiency is only 1 or 2%. So in the beginning, they were using platinum palladium catalysts for this, but they were getting fouled very quickly. Although they were able to convert sulfur dioxide to sulfur trioxide, they were prohibitively expensive because these are all precious metals. But then that has changed in the last 20, 30 years by the discovery of a catalyst, it is a potassium vanadate, KBO3. What do you think the crystal structure of this compound be based on the solid state chemistry that we have learned? Then you have potassium B and oxygen in 1:1:3 ratio. What is the most likely structure of this catalyst? There is a reason why we talked about solid state chemistry, right? We're now bringing all this into this picture here. Anyone? What is the most famous crystal structure that has a ratio of 1:1:3? ABO3 type.
Is it the perovskite structure?
You are absolutely correct, though. That's correct. That's a perovskite structure. So KBO3 is a potassium vanadate. This is a vanadium in 5+ oxidation state, potassium 1+. That's why we teach nowadays solid state chemistry, because at the end of the game, that you need to really go back to your database, bring different materials, keep testing, and suddenly one thing works. And what worked in this like a miracle was the potassium vanadium oxide, which is a perovskite structure. So the way it happens, this is again a proposed mechanism. Don't ask me for an evidence. Don't ask me for a proof. I have neither. But this is a speculation based on educated guess. Because most of these potassium vanadates, when you heat it, they lose some of the oxygen and make what we call oxygen deficient perovskites. In all oxygen deficient perovskites, you have a mixed valence of 5+ and 4+ vanadium. So in fully oxidized form of KBO3, we have the vanadium exclusively in 5+ state. But when you have oxygen deficiency, some of the vanadium gets reduced from 5+ to 4+. This mixed oxidation pair of 5+ and 4+ is found to be critical for the oxidation of sulfur dioxide to sulfur trioxide. So let me give you the mechanism here. So if you take 1/2 of O2, and when you have oxygen deficient perovskite, you have some of the vanadium in 4+ state. That vanadium is now oxidized to vanadium 5+. You see the redox chemistry that we have learned, now it's coming into play here. So, and then what happens is sulfur dioxide gas reacts with the oxide ion of the perovskite and the vanadium 5+ that we have to make SO3 plus vanadium 4+. That vanadium 4+ again goes back into the first step. So these two steps repeat infinitely, and in the net effect is sulfur dioxide reacting with the oxygen. They're not reacting directly. Potassium vanadate is a mediator. So it just makes the oxide ions. These oxide ions now react with the sulfur dioxide to make sulfur trioxide. So this has changed the game for the production of sulfuric acid. Once you have the sulfur trioxide, you add water, you make what we call intermediate oleum, but oleum finally breaks down to sulfuric acid. So this is how the second most largest quantity of chemical that is produced in the world uses a perovskite catalyst for it to happen. See how beautiful everything falls into place here. How the inorganic chemistry changes the shape of the world. These two processes, the Haber process and the sulfur dioxide oxidation alone, contribute to maybe $1 trillion economy. You cannot survive, humanity cannot survive without these two important compounds, ammonia and sulfuric acid. All right, questions up to this point? The next important material that we'll talk about is what we call Fischer-Tropsch synthesis. In fact, in my opinion, if you ask me, these two people deserve a Nobel Prize. But unfortunately, they did not get. Um, I don't know why, but I can tell you the situation. Maybe you can come up with a conclusion here. Fischer and Tropsch were working as chemists in Germany during the World War II time. So during the World War, when Hitler was ruling the country, the entire world placed an embargo, oil embargo on Germany. So Germany was completely cut off from the oil supply. So they were being squeezed. So the only choice Germany had was to make their own oil. They don't have any oil wells, but they have a lot of coal mines. So these two great scientists developed a process so quickly and made Germany completely independent of external oil during the Second World War. Amazing discovery, pure science, but they didn't get the Nobel Prize. Maybe, I don't know, you can think about a reason why that may be the case because of the politics of the world at the time. All right, so the way it happens here is this is a very simple process. The first thing that you do is you take carbon, which is the coal, and you react with water vapor to make carbon monoxide and hydrogen. I'm just giving you a very simpler breakdown. Of course, the actual mechanism is very complex. Uh, you can go onto the websites of fischertropsch.org and you will have all the catalysts that have been tried for this reaction. But I'm just giving you an overview of how this reaction is carried out. Then what you do is you take carbon monoxide and H2 gases, pass it through a catalyst. The catalyst here is cobalt on titanium dioxide or iron on silicon oxide or aluminum oxide. So when you pass carbon monoxide and hydrogen, this is called syngas. These are all the technical terms we use in industry. So this is a syngas mixture. And when you pass the syngas over the catalyst, you get a variety of hydrocarbons. By changing the conditions, the temperature, and the pressure of the gases, you can make anywhere between methane, ethane, and all the way to octane. Most of the Fischer-Tropsch processes give you linear chain hydrocarbons, and you can do isomerization on the octane to get an octane and isooctane, which is what the gasoline is. By changing the conditions, you can also make diesel. And by changing the conditions, you can also make tar, all kinds of petroleum chemicals. So you don't need oil here. You can make oil, you can make diesel, you can make tar, you can make gases, everything just by converting carbon. So this is what we call the CTG, carbon to gasoline technology. So if the oil prices go up in the world, America is lucky because we have coal reserves that will take us for the next 3,000 years or maybe more. So we can use some of the coal that we have, convert that into carbon monoxide and hydrogen, and do this process and make petroleum diesel. In fact, we used to make in Brownsville, Texas, around 1970s, I think, at Jimmy Carter's time, I believe, we used to make petroleum. But what happened was all the companies, the actual major gasoline companies, people say they have conspired. I don't know whether what happened really, but that plant, after 2-3 years, was purchased by a major petrochemical company and dismantled it because they didn't want anyone to make gasoline because that is going to hurt the pockets of the major petrochemical companies. But, you know, there's still countries like South Africa, they don't import any oil. All the oil they make is from this process called gasoline, Fischer-Tropsch process. So there is a company called Sasol. So if you can Google that word, Sasol in South Africa, they make exclusively they don't import a drop of oil from Gulf or any other countries. So all that they need. So they are extremely self-sufficient. And if the price of the gasoline goes above $4 or $5 in this country, perhaps we may come back and revisit this, because when the cost analysis was done last year, we did with chemical engineering students, we found that you can make gasoline for about 2.8 to $3. So that's the economic analysis as of now. So if your petroleum is $5 per gallon, you can come back to this technology. The most important thing we need to do is work on the catalyst part here. And unfortunately, these things require temperatures in excess of 200 degrees Celsius and pressures in excess of 40 atmospheres. So you can't do this reaction in open containers. So you need to take the carbon monoxide, hydrogen, pressurize them to about 400 degrees Celsius and increase the temperature and use some of this catalyst. I like this way, like iron and cobalt. Some people have used nickel, some people have used ruthenium, rhodium. If you go to that website, fischertropsch.org, you have the entire literature that has been going on for about 80 years. So in about 1940s till now. That website gets updated every week with any new discovery of the Fischer-Tropsch. So this is going to be one of the important technologies that you may want to keep in mind, because, who knows, there may be a point in your life where the petroleum might be so expensive that you want to go back to this plant. In fact, I heard that Exxon is building some of these plants in Gulf. So they got the license to manufacture some of the coal to gas technology. But the world leader, of course, is the Sasol from South Africa. So you can do your own research, but I'm giving you the importance of inorganic chemistry and the crystallographic forms. For example, when you go to titanium dioxide, there are 5 different crystallographic forms for titanium dioxide. 2 most important them are the anatase and the rutile. Here, the titanium dioxide is anatase form, not the rutile. Rutile doesn't work well. So these are all small things that when you get into the details, everything becomes extremely interesting. And the size of the cobalt particles is very important. The concentration of the cobalt is very important. And what else you can do into the titanium dioxide that can improve the efficiency? There's a huge amount of research that's going on, especially in countries where they don't have oil resources. Fischer-Tropsch plants are not cheap to make. So China, for example, is dependent on oil from Middle East and US and other places. What they have been doing in last 5 to 10 years, you can go back and do all the research, they started building these plants. These are not cheap. I mean, they take about $5 to $10 billion for a small plant. I heard that they built about 6 or 7 of these plants, and they are building more and more because China has vast resources of coal, and they would like to use that and make oil rather than importing oil from other countries. So you see the point is, the critical part is the catalyst here, which is the inorganic part here. That's where the inorganic chemistry plays a very important role. All right, so this is one important, of course, there are countless number of examples, so we can't be spending the entire thing. So let me give you one last example, very important one, as you all know, terephthalic acid is very important for the making of the plastic bottles, right? Polyethylene terphthalates, PET bottles, are used extensively for storing beverages and water and all that stuff. So to make that, what happens is you need to have paraxylene and oxidize it to what we call terephthalic acid. The problem is whatever xylene that we make here comes from petroleum. So most of the plastic bottles that we use today, the source is from petroleum. So in petroleum, what happens is you have all three xylenes. You have the alpha, meta, and para. So how do we separate these three and get exclusively the paraxylene, and then you want to do an oxidation right away on that to give you terephthalic acid. So in reality, we have all three xylenes mixed in the petroleum refinery. So what they do here is they use the zeolite catalyst, which is sometimes called ZSM5. This is one of the very critical discoveries, very extremely important milestones in catalysis. This was discovered accidentally in 1962 by the Mobil Oil Corporation. And this, I would say, after ZSM5, there was no development in the petrochemical industry. All the other developments are very minor. This is the completely game-changing catalyst. The ZSM stands for the zeolite Saucony Mobil. So these are all the acronym for this. Then there, of course, ZSM5, ZSM7, ZSM70, ZSM100. There are a variety of zeolite catalysts that have been developed, but this is the primary thing. So the key aspect here, what happens is we have this catalyst. Remember we talked about the zeolite catalysis in the past. So we have these channels in the network, open framework. You can fine tune these channels such that when you have a mixture of these three xylenes, pass it through this. Remember, this has the smallest cross section, the para, while the alpha and the meta have a very large cross section, if you look at the cross sectional area of the molecule. So when you pass these three mixtures into this, only the paraxylene comes out because of its smaller size, smaller cross section, and the meta and the alpha are set aside. But when you have the protonic activity of the zeolite, because zeolites are strong acids, we talked about that in the beginning of the class, this proton, this acid, can do the isomerization again on this alpha and the meta ones and keep converting the alpha and the meta to paraxylene, because only paraxylene can move through the channels. So this is sometimes called molecular traffic control catalysis. So it's just like a traffic. You know, when you have 3 or 4 things come in, this zeolite not only sieves it out, but also converts the other 2 and efficiently make the entire thing completely paraxylene. Once you have the paraxylene, you can oxidize this very easily, and cobalt manganese acetates. That's again another area of catalysis. So the co-catalyst of cobalt and manganese. So that will give you terephthalic acid. I'm sorry, we just passed 1 minute about the class. That's about what I would like to do in the heterogeneous catalysis. I think I gave you a flavor of heterogeneous catalysis. I want you to go back and read the topic again. Some of those examples from my own research a long time ago. I was so fascinated by this topic when my professor presented this to me about 40 years ago. Then I thought I should do research in this area, and I did work in this. Although I haven't talked any of my research here, these are all industrial processes, just to give you a flavor. All right. Any questions before we close the topic? Just to remind you again, we have the sample exam on 15th. There will be no class. On 20th, send me an email if you have any questions. So there will be no regular class. On 22nd, we have the final exam, and the following week we'll start the lectures on superconductivity and magnetism. If there are no other questions, thank you very much for coming to the lecture. We will see you again next time. Bye.